Hi there, folks. Today we're looking at graphing polynomial functions, and really this is kind of an extension of what we've already done in terms of graphing. We've drawn quick sketches of these things where we identified, the X-Intercepts and the kind of the path that the function follows. We're going to do that same kind of thing here, but we're going to use graphing calculators and computer programs to kind of fill in the gaps to make these a little bit more of an accurate representation of the graph, all right? So yeah, we're going to start with this idea of, okay, what does this thing kind of look like? What is it supposed to look like? And then we're going to use the calculator to give us a more accurate depiction of that path of the function, of the shape of the function. And then we're going to identify all the important points on the function, all right? And this is slightly different than the way we've graphed a lot of other things, because instead of having like, exact values marked out on our graph, okay, because some of these values get really big or really small, all right, we're just going to draw kind of a model of this thing where we label the important points but don't necessarily count to them, okay? And you kind of see what I mean as we go through this. It'll be slightly different. We won't have like the little tick marks on our graph, but we'll still label those things using ordered pairs to show the accuracy, to show exactly where this thing kind of goes to, all right? For example, if I look at this first one, so kind of looking at this from the approach of what we already know, in terms of drawing a quick sketch of this thing, what we already know how to do is when it's in factored form like this, we can easily find the X-intercepts, all right? The computer or the graphing calculator will also be able to do that for us, but a lot of times it's easier to do by hand when it's in this format. So we say, hey, if this thing equals 0, let's find the X-intercepts. I've set each of these factors equal to 0. And I solve each here. This one I would add the 1. Here I would add the 3. And here I would subtract the 2. So I get these ordered pairs, 1, 0, 3, 0, and negative 2, 0. And then from here, I'm not going to draw on my graph off to the side over here. I'm just going to draw a quick sketch maybe over here, an unofficial kind of sketch. And so if I kind of look at this unofficial sketch, I've got, let's see, a 1, a 3, and a 2 here. I also kind of know about the path of this function by looking at the end behavior. And so when I look at the end behavior on this one, remember, I only want the first term of this thing multiplied out, so I only multiply out the first terms, okay? And each of these binomials to the first power, so it's just x times x times x, which is x cubed. So if I were to multiply this out, I would get a 1x cubed. And again, if I continued to multiply out all three of those binomials, which I can do, I would end up with a 1x cubed and a bunch of other terms. But again, I only care about the first one if I want to know the end behavior. And so an odd degree on this one, if the degree is odd and the leading coefficient is a positive, it means that this end is going to go down and this end is going to go up. Okay? And then based on how many times I got each of these answers, because each of those binomials only occurs once, I get each of those answers only once, which means in terms of multiplicity, the path has to be something that kind of goes like this. Okay? And I know it's supposed to look kind of like that. Now, there might be some details in there that I'm missing, so maybe it could do something like this. It's possible that it kind of goes like this, and then it has like an inflection and does all kinds of stuff like that. For this particular example, it's not going to do that, all right? But there might be some details that we don't know about that'll kind of appear as we graph this thing using some of our graphing utilities and that kind of thing, our calculators and the Desmos is the other one that we'll use, okay? And so we have this idea of a quick sketch. That'll help us when we look at the calculator or when we look at the computer to make sure I find all those important values. See, right away, I can see there's a relative maximum between the negative 2 and the positive 1. There's a relative minimum between the positive 1 and the positive 3, okay? So let's go look at the graph of this actual thing. And so from the graphing utility, here's what we've got. We looked at this and saw that, the graph our sketch wasn't too bad. It does go up like this and then comes back down and then back up again. Okay, so our kind of quick sketch was good. We can make it a little bit nicer as we draw this thing. So now I'm translating that. And again, we draw the quick sketch just to kind of give us an idea of the shape of this thing. And then to show all of these different pieces, we're just going to label them. So like here, I'm going to label this, and instead of having these little tick marks all drawn, I'm just going to label this ordered pair negative 2, 0. And if I do the rest of the x-intercepts here, let's see, that's 1, 0. This one was the 3, 0. And again, we already knew these even before we looked at the actual graph. But what the actual graph then gave us was these guys. It gave us this relative maximum here, and that was the ordered pair negative 0.786, comma 8.209. And then down here, this relative minimum, again, we got a 2.12, negative 4.061. Okay, and so we kind of copied all those things down from the graph, and now we put them on here. And again, the graph isn't completely accurate in terms of I didn't draw all the little tick marks and kind of show this thing around 8.2 for that first relative maximum. I show the accuracy by writing an ordered pair. Okay, so I draw a sketch that gives me an idea of the shape of this thing, and then I give it accuracy and I give it more context by including all of these really special points and showing exactly where those things are. Okay, and so even if this thing isn't necessarily drawn to scale in terms of the actual curve and in terms of the relationship between the x and the y axis and how far apart those little tick marks are and that kind of stuff, that's okay, because I still have an idea of the accuracy of this thing based on the ordered pairs that I have written down. Okay, and you can even tell in this drawing right here from this relative maximum down to the axis, that's 8 units, and here, that's negative 4. Really, if I was drawing this to scale, that negative 4 should probably be up here somewhere, okay? But again, we understand that this is just giving us the shape. The accuracy is based on the values I have written. So we're not necessarily drawing it to scale. We want a good representation of this thing, okay? If I look at this next one, same kind of thing, except this time I don't have this thing in my factored form. I could factor it. All right, so I could try factoring it and finding the x-intercepts and that kind of stuff. But really, we don't need to do that. We just need to understand, okay, an x to the 4th function, I kind of have an idea of what that might look like. So if, again, I only look at the first value here, I already know the end behavior. And just based on our knowledge of some of these other things that I've dealt with, if I know the end behavior, so even degree, so they're both going to open up or down, since the leading coefficient is positive, both ends are going to open up. So I know both ends are going to open up, and just knowing what I know about these different functions, well, this thing might do something like this, okay? Or maybe it crosses the axis more times, it might do something more like this, okay? Or it could do something like this. So again, I have a general idea of what this thing looks like or what it could look like, but now I'm going to use the graph to kind of get a little bit more detail on those things, okay? So I'm going to punch this in, I'm going to find all the important values, including the x-intercepts, and then I'm going to draw a more accurate depiction of this thing, okay? And so from the graph, I found out that, my quick sketch here wasn't exactly right. Instead of having 2 relative minimums, I only had 1. The function did still have more turning points, but it kind of went like this. It kind of came down this way, and then curved that way, and then curved back down, and then back up. Okay? And so I still get more curvatures, but this guy wasn't extended out as much as we thought it was going to be. Instead of this thing going like this and then coming back up and down, it kind of just curved like it was going to start back up, but then went down instead. Okay? And so again, we knew where to look for that thing. We knew to look somewhere towards that left-hand side, that there was going to be some kind of curve we needed to mimic. Well, it just didn't ended up being exactly the way we thought it would be. Okay, and then from the graphing device, we just calculated or found all of these values. So we had this guy that was at 20. Sorry, I looked at the wrong note that I had. This one was 0.86, comma 0. This other x-intercept over here was 3.9, 0.97. I rounded it off just a little bit, comma 0. And then the relative minimum down here, that was a 3, negative 25. Okay? And so the only value that surprisingly came out nicely was that relative minimum. The X-intercepts, we wouldn't have been able to find those by factoring, so the calculator, the computer really helped us out on that one, okay? So now, again, even though this thing isn't drawn to scale, if it was drawn to scale, this relative minimum would be way, way, way down here, probably even further down than that. But instead of having this huge graph, I condense it a little bit. I don't quite draw it to scale, but I draw an accurate representation or an accurate enough representation of the shape, and then I add accuracy to it, I add context to it by labeling all of those special points, okay? If I look at this one, this is one where I can get a little bit more information before I graph it. So once again, I could set this equal to 0 because it's in factored form, and I could find the x-intercepts ahead of time. Okay, so if I set each factor equal to 0, here I get x equals 0, so that's the ordered pair 0, 0. Here I would add the 6 and get x equals 6. That's the ordered pair 6, 0. But then there's also something special here. Because of this guy, because there's an x to the first out here, I'm going to get that answer once. That's multiplicity. But look at this. Because there's an x squared here, it means I would get this answer twice. Okay? And so that idea of multiplicity gives us a little bit more information about the sketch of the graph here. Again, looking at just the leading coefficient and the degree, if I were to multiply out these things, so that would be just the first terms. So this guy squared is an x squared, and then times the negative 2x. And so, again, just looking at those first terms, again, if this guy was squared, it would be an x squared, and then times just this first term. So I just look at all the first terms and I multiply it out. That gives me the first term of the overall polynomial. It's a 2. Reading is hard sometimes, right? A negative 2x to the third, okay? And again, if I were to completely multiply this thing out, which I could do x minus 6 times itself, multiply all that out, then distribute the negative 2x. If I did that, I would end up with a negative 2x cubed and a bunch of other values. But again, I don't care about those values. I just wanted the first one. And so because it's a cubed function, it's an odd function with a negative leading coefficient, I know that this end is going to go up and this end is going to go down. Okay? I also know these intercepts here, this guy and this guy. And I know a little bit more about this because as this thing comes down here, and let me move this guy over a little bit. As I approach this first value, I'm going to go through the x-axis because the multiplicity is odd. But right here, this one I'm only going to touch the x-axis. And that has to deal with this guy right here. That idea of multiplicity, remember that when multiplicity is odd, it tells me to keep going through the axis. Okay? But when the multiplicity is even, it tells me to do a relative maximum or relative minimum at that point. It tells me to just touch the thing. Okay? And so the end behavior all matches up. I kind of have an idea what this graph looks like, but now let's go get a more accurate representation. Okay? And so for this one, I found out that my graph wasn't in too bad a shape. I have these values here, but in terms of the shape, this thing comes pretty steeply down and then back up and down again. Okay? And so we get this slightly more accurate representation. The thing that really makes it accurate, though, is all the values that I got from the graph. And so right here, this was the ordered pair 0, 0. Again, I already knew that one. This one was the ordered pair 6, 0. But then I also was able to pick up this relative minimum at 2, negative 64. Okay? And so again, I have a sketch that represents the shape of the graph. I have all these points that represent the accuracy of the graph and all those special points that I need, okay? And not only that, but now I can see the relative maximums, the relative minimums. I would be able to interpret this in a little bit of a better way, okay? If I look at this one, once again, I could try to solve this thing by factoring, but let's let the calculator do the work for us. Now that we have a better idea of what these things kind of look like, again, maybe I look at the end behavior on this one because I've got a 1/4 x to the fourth. Again, I only look at this first value. I don't care about the rest of them written. I know it's only one other one. But I just look at this guy and say, hey, the degree is 4, so an even degree, they're both going to either open up or down both ends. And because the leading coefficient is positive, I know that both ends are going to open up. So right away, just thinking about the quick sketch of the graph, both ends open up. And again, I don't know about the details. Maybe this thing goes like this, okay? Maybe this thing goes like this. Maybe it does one of these things, all right? Maybe it does one of the things that it did before where this thing kind of curves this way and does something like this, okay? Well, we know that it's going to be something in that vein, but we're going to get a more accurate representation by graphing this thing using a calculator, using the computer, okay? So let's go take a look at the graph this time. And so after looking at the graph, I found that this thing was perfectly symmetrical. And so I had something that kind of looked like this, where I had one end that went like that, and then a second end that did the exact same thing, okay? And everything was symmetrical as I labeled these values. So like the X-Intercepts, this guy was at negative 2.828, comma 0. The other one over here was at a positive 2.828, comma 0. Of course, this guy in the middle, that's at 0, 0. And then I identified these relative minimums, and those were also symmetrical. This one was at negative 2, negative 4. And this one was at positive 2, negative 4. Okay? So again, I get the shape of this thing. I draw a quick sketch that represents what this thing should look like, but then I give it accuracy, I give it context by labeling all of those crucial points, okay? Relative maximums, relative minimums, X-intercepts, Y-intercepts, okay? If I look at this guy, so this is kind of using polynomial functions to model a certain situation. So in something like this guy, so I have a piece of cardboard that's 20 inches by 36 inches. So let me draw my piece of cardboard, of course. And again, it was 20 inches by 36 inches. And what I want to do is I want to cut the corner. So I'm going to cut a square out of each corner. And I want to cut all of those squares the same side. And then I'm going to fold up the tabs that are left to create a box with no top. Okay? And so the idea here is I'm cutting away at this corner. And I'm going to do the same thing to each of these corners. Okay? And I want to cut the same amount, the same size square from each corner. Okay? And so what happens is if I were to cut this, all right, imagine that this piece on this end, if each of these was gone, just pretend they're not there anymore, okay? What it does is it gives me like these little tabs right here. If I kind of draw that line, we can kind of see this guy right here as a tab, okay? And if I were to fold that tab up, it would give me one of the sides of the box. Same thing here. If I were to make a fold right here and fold that side up, that little tab that's there, okay, it would give me another piece of the box. Same thing here and the same thing here, okay? And so maybe it would be better if I redrew the picture. But essentially, once I cut those little squares out, what I have is something that looks more like this, okay? And so here's what I'm talking about in terms of these tabs. So like this guy right here, if I were to kind of fold that up, that would be one of the sides of my box, okay? And hopefully you can kind of visualize that, kind of making folds and each of these things that I have squiggly lines on. Imagine those folding up off of this paper. Now I'm looking down into the bottom of the box, okay? And so what I want to do here is I want to calculate the volume of the box, but I want to maximize that volume, all right? And so I have to determine, well, what size cut should I make? And so the idea here is if I call that X, okay, so the size of the cut is X. I could visualize it over here as well, X, okay? That's the thing I have to be smart about. I have to make the right size cut in order to make the volume of this box the most it could possibly be, okay? And so now I need to think about the dimensions of the box itself. See, once I fold those tabs up, the box is not going to be as big as the original cardboard, okay? Because again, if all of these pieces represent X out here, okay, that means that the bottom of the box, the length of the box is this purple piece right here. Well, it was 36 inches, right? But then I cut a square away from each end. I cut X off of one end, and I cut X off the other end. So what I did was I reduced the length of this thing to 36 minus 2 of whatever I cut off, okay, because I cut it from each end. Likewise, the width of the box would be 20 minus 2x because I cut the same amount off of each end. And to think about the height of the box, as I fold up these tabs, think about what the height of the box would be. Well, that's the value of x, okay? So the height of the box is going to be whatever the size square that I cut, okay? And so if I think about this from the perspective of length, width, and height, the length of this thing is 36 minus 2x. The width is 20 minus 2x. And the height of the box is x. And so if I want the volume is length times width times height. And it doesn't matter what order I do these in. If I was writing a polynomial, I'd probably write it like this, with the x out front. And see, this is a situation where I can find the x-intercepts myself. I can find those as x equals 0, and x equals an 18, and x equals a 20, all right? Just by setting each of these factors equal to 0. And so if I want to think about maybe a quick sketch of this thing, I know what's going to happen when I graph this thing. I'm going to have these values at 0, 10, and 18. And if I multiply out just the first values, and again, these are not written in the proper order, but it would be these guys. So all the x's multiplied out, that would give me a positive 4x cubed. So if I multiplied all this out, I'd end up with a positive 4x cubed written first with a bunch of other terms. I don't care what they are. But that gives me an idea of the end behavior of this thing. It's going to go down on this end and up on this end. So kind of know that it's going to go like this. Okay? And just having a quick sketch of that thing, that's going to help me when I go to graph this. Okay? So I go and graph it. Let's take a look at the graph. And so once again, comparing that graph to what we have drawn, the graph looks like kind of what we have drawn. However, if I didn't know what this thing was supposed to look like, that graph wouldn't have made any sense. So that's why we want to have an understanding of what it should look like, so I know where to look, I know how to look, okay? And so the actual graph of this thing, if I draw a more accurate, well, I guess I can use the one that I have here. So here I had a 0, 0. Here this was the 10, 0. And this was the 18, 0. But then I was also able to identify these relative maximums and minimums. This one at 4.127, comma 1345. This one down here at 14.54, comma negative 913.6. And see, the thing here is that the question asked me to maximize the volume. Well, this graph, the y values on this graph represent the volume. So if I'm thinking about it, here's the highest y value that I can see, but this thing keeps going, so there's a y value here that's higher. And if this represents volume, doesn't the volume keep going up forever? So it doesn't go to infinity? All right? And the answer is, if we're purely looking at the graph, the answer is yes, the volume goes to infinity. However, we have to look at the context of the situation. Part of this graph doesn't live in reality, okay? If I could cut this box in any way, yeah, I might be able to get an infinite volume as I enter into an imaginary realm, okay? But in reality, this graph, I can only use pieces of it. And here's why. When you think about cutting the box, think about the biggest cut you could possibly make before you would cut the whole way across and not have a tab that you could fold up, okay? See, right here, the box is only 20 units wide. So if I make a cut of 10 from one end and a cut of 10 for the other end, what's going to happen to my box? Yeah, that end is going to completely fall off, okay? I won't have a tab to fold up. I won't even be able to make a box, okay? So the cut that I make has to be less than 10. Well, when you look at that from this perspective down here, when I look at the graph, less than 10 means that the only feasible values for my graph are between 0 right here and 10 right here, okay? Which means if I want to maximize this box in reality, I can only use the values between 0 and 10, which means I want that relative maximum, okay? That relative maximum represents the cut that I could make and the maximum volume that I could have. Okay? Every other piece of this graph is outside the realm of possibilities, all right? Because they're outside the realm of what I could physically cut off of the end of this cardboard, Okay? And so the question, to answer this question, says, hey, what's the cut that should be made to maximize the volume? Well, that's 1.27 inches. So each of those little boxes should be 1.27 inches. Or a more realistic way of saying that, it's about 4 1/8 inches. Okay? 1/8 being 0.125. Okay? And so that's what I would do. The maximum volume, the actual volume that I would get, would be this guy. But again, the question didn't ask me to give the maximum volume. It said, what should I do to maximize the volume? I should cut about 4 1/8 inch for each of those little squares. Okay?